So welcome everyone to this public lecture as part of Science Week. My name is Geordie Williamson. I am the director of the Sydney Mathematical Research Institute that is hosting this event. So we're delighted to see you all here today. I'd like to start off by acknowledging the Gadigal people of the Eora Nation, on whose lands we are working and studying and learning, and acknowledge that learning has been taking place for many, many tens of thousands of years, where we're standing today. So now I should introduce Andre. So Andre is a mathematician, logician, computer science. So he works in this kind of fascinating interface between mathematics, logic, and computer science. So, if you're a mathematician, you know about set theory. And if you're not a mathematician, you might know that we, as mathematicians, kind of care about the fundamental axioms with which we work. And if you ask me what axioms I work with, I kind of know a parrot response to this question. I say ZFC with choice. Yeah? But I don't understand what that means. I've got no idea what that means, and I'm quite happy being a working mathematician. And that's the way that the vast majority of mathematicians operate. But it's very interesting because over the last, 40 years or so, as we've tried to use computers to check proofs, we've discovered that ZFC with choice is not the greatest foundation. And Andre is an expert on type theory, which is an alternative foundation for mathematics. So he got his PhD from Carnegie Mellon University in, I think, around about 2000. And so CMU is one of the real world centers of kind of computer science, robotics, AI, and foundations of mathematics and logic. And he's been working in this space ever since, and I think he's one of the best explainers of kind of these foundational questions that most mathematicians ignore. And he's giving a series of lectures at SIMRI about the foundations of proof assistance, which have, the first lecture was fantastic, and I think the next lectures will also be very good. So it's a real pleasure to have Andre here today, and he, I think, is talking today nothing about what I've just been talking about, beautiful experimental mathematics, and try to give some of the joy of discovery in mathematics. So it's a delight to have you here in Sydney, Andre, and Andre's brought along his family, so welcome, and we're delighted to have you.
Thank you for inviting me. It's a pleasure to be here. It's the first time that I'm down under, and in this hour, or a little less than an hour, I hope to take you through a journey showing how mathematics can be exciting and interesting, even where you would do, judging from what you learned in high school, it seems very drab. And the way we're going to do that is we're going to use computers a lot, because computers they got very, very fast, and so we can calculate amazing things, and you'll see what I mean. So first, though, I want to make you all feel like you are still in high school. So let's recite together the formula for the solution. So I don't know how you do it in Australia, but in Slovenia, it starts with x12 equals, now you go, minus. Congratulations. I see the education system in Australia works. So this is what you recited, right? But seriously, what's this good for? I mean, why does everybody have to learn this in high school? It's a bit strange. And in fact, there's a funny story. I once asked a classroom full of math majors, I think they were freshmen at my home university. I said, well, does anybody's parents here require working knowledge of this kind of math at their work? And one student meekly raised her hand and she said, yes, my mom is a math teacher. So that was it. There was a lot of laughter. But seriously, solving equations has interested humanity for a very long time. Quadratic equations like these, the Babylonians knew how to solve them. That's 4 millennia ago. And more than once, the desire to solve equations led to amazing new discoveries and new kinds of numbers and so on. So let's first go through a little bit of history. So for instance, the ancient Greeks already knew that if you want to calculate the length of the diagonal of a square, you set up a quadratic equation using Pythagoras' theorem, and then you need to solve this equation. And nowadays, this is easy, right? You would just write, well, of course, x equals square root 2. However, the square root radical, the symbol that's at the top of 2, the radical, that's a 16th century discovery. That only got used in the 16th century. So Greeks didn't actually have any way of writing down this number, and they thought it was a very strange number. They called it irrational, but not because it's insane. They called it irrational because it's not a ratio of two whole numbers. So that was an early discovery of a new kind of number, an irrational number, just from the desire to solve an equation. Okay, of course, mathematicians didn't stop here, right? They would go on. So how about the cubic equation? Would anybody like to recite the formula for the solution of a cubic equation? There are a lot of, I see there are a number of mathematicians here, so I'm going to ask, does anybody know the formula for the cubic off the top of their head? See, that's because it's a bit more complicated. So you first have to calculate P and Q, and then you introduce C, and then you have a zeta, and then your solutions look like this. Thank God we're not trying to teach this to our kids. Okay, so in today's notation, this is kind of complicated, but this was really complicated when it was first discovered. This was research math. It was in Italy in the 16th century. So the Italians worked on this a lot, and they knew how to solve the cubic equation. And it's really a fascinating story. In those times, mathematicians would wager money, reputation, and their academic positions on competitions. They would compete each other. So they would present themselves with lists of problems, and whoever won a large amount of money and prestige and the academic position. So you could lose an academic position if somebody smarter than you showed up. So that was no joke. So you can imagine that they kept the formula secret. And there is a fascinating story of intrigue and treachery of the 16th century Italian mathematicians, which you can look up. There is a very good channel, Veritasium, I don't know if you know it, where this is explained. So I recommend it highly, especially if you are tired of 16th century Italian lovers' tragedies. So this is a different kind of story. Okay, so the cubic was very important also because it led to discoveries of new numbers, but just, so let's have a look at that, okay? So it led to the invention of complex numbers. So let's start with the equation x squared minus 1. Okay, that's an easy one. It has two solutions, minus 1 and 1. So those are the zeros of the polynomial x squared minus 1. But what happens if you change the minus 1 to a plus 1? Well, then the solutions disappear. And they're not there. And when people solved quadratic equations, nobody felt the need to imagine that this thing still has a solution. Obviously, it doesn't. There is no number such that when squared, it gives you minus 1. However, when the cubics came along, the complicated formulas that I showed you, what people noticed was that you had to deal with these strange square roots of negative numbers that don't exist because they canceled out and gave you an actual solution. So it was a strange thing where something that shouldn't be there was playing an important role in the computation. And so eventually they came to terms with it and they said, okay, let's calculate with them. So the numbers that we get are called the new kind of number that was discovered this way was called an imaginary number. And this imaginary, the word imaginary, that was introduced by Descartes. And the name itself shows you how difficult it was for mathematicians to accept the new kind of numbers. So let's have a look at how they arise. So instead of having just the real line, we also imagine having another line, which is called the imaginary line. And then the complex numbers are combinations of the real and the imaginary ones. And so if you change, so let's change that coefficient -1. Let's change it to 1 to see what happens with the zeros. Okay, so this is today's technology. So as you go, whoop, and they go to the imaginary line like that. And that was the invention of square root of -1, which is I. By the way, why do we write it I? That's because when they had a square root of 1, it was really confusing as to which of the two square roots you should take. And so to prevent mistakes, they started writing down I for one of them. So that's a second kind of numbers that was invented so that equations could be solved. And we're going to work with complex numbers. So where do things go on from there? Well, the next one is the quartic, right? Okay, this one we're going to skip because this is like Rocky IV. Nobody knows, nobody remembers. This is just more 16th century Italian drama, okay? So we'll skip that one. Okay, how about Rocky V? Well, actually something very interesting happened. People tried really hard to come up with a formula for solutions of the 5th degree equations, so zeros of a 5th degree polynomial. And nobody could come up with a nice formula that would always work using the basic operations, plus, minus, times, division, and the roots, so square root, cubic root, and so on, 5th root in this case. And they just couldn't find one. So that was mysterious, and then people started to think maybe there isn't a formula like that. And in fact, still an Italian mathematician, there will be lots of Italians today. So an Italian mathematician, Ruffini, wrote a 500-page monograph explaining that such equations cannot have solutions written in terms of those operations. But people had a hard time believing exactly whether he was right. I mean, they were respectful and so on. So it was difficult. Today we know that he made a mistake. Okay, so there was a mistake in his work. And then a little later, a Norwegian mathematician, Abel, came along, and he published a very short proof. It was only 6 pages long. And the reason it was only 6 pages long was not only because the proof was so brilliant, but it was also because he paid out of his own pocket for the publication of the proof, and so he was trying to save money. In fact, I couldn't find the original. Probably they are quite expensive nowadays if you can get your hands on one of them. This is a longer 20-page version that you can actually find in publication. Okay, so it's in French. So that was really a big thing. Conceptually, this is important. How do you prove that you can't do a certain thing? How do you show that you can't write down solutions in terms of certain operations? That requires a lot of original thinking. So at this point, we're entering development of mathematics, which is more than just understanding that there are new kinds of numbers. This is about deep understanding of what the structure of those numbers is. So we're now moving ahead. And this is, I think this is the 18th century, if I'm not mistaken. Maybe 19th. No, Abel is already 19th. Okay, so how about all the other higher orders? So we could go on, right? 6, 7, 8. So by intimidation, we go on and on and on. Well, these turn out not to have any nice formulas in terms of plus, minus, times, division, and roots that would present the solutions. The work that was needed to do all these other ones was done by a French mathematician, Galois, and he was not the ordinary kind of mathematician. He was repeatedly arrested for political activism in the 19th century France. He got kicked out of École Normale, the school, and he died at the age of 21 in a duel, which is a pity. Who knows what else he would have done. But he laid out the foundation for showing that all these higher order equations can't have the solutions written in a certain form either. Now, of course, does that mean we can't solve these equations? No, it just means we can't write them down in a way that the 16th century Italians would expect. But nowadays, we have a much wider understanding of what a formula is. Nowadays, a formula is a program that can be run on a computer, and we can write down programs that solve such equations. So I'm going to use software, which is open source software that is easily available for scientific computation. So that's where I get my solutions from. And then some image manipulation and movies and so on. And it's really not a lot of code. So to prepare everything in this lecture was just a couple hundred lines of Python and C code. So it's not that much. It took a little longer to compute, but nevertheless. So our understanding of what a formula is has developed through the desire to compute. So here's my first answer as to why do we want all these solutions to equations. Because indirectly, they led humans to think about what does it mean to compute. And our current best knowledge of what it means to compute has completely revolutionized humanity because it's computers, right? So it's not, the 16th century Italians, they were onto something. Okay, but let's do something fun. Let's then solve all these equations because we can actually compute the solutions. So let's do that. So here's just some 5th degree polynomial. And these are the orange dots are the solutions to this one. Okay, so there's 5 of them because it's the 5th degree. And so how about the 6th degree? Well, here's the 6th degree, and there's 6 of them. And one thing we can do is we can start noticing things. Okay, so here's 7th degree. So one thing I would like you to notice is I'm going to ask, so here's something I tell, okay, I'm going to ask you something that you should never ask as a teacher. Do you observe anything interesting about this picture? When I teach future math teachers and they ask the question, I go up in flames, and it's like, that is the dumbest thing you can do to your students, because they're going to say, yes, I can observe a horizontal white line, and then what are you going to say, okay? But do you see the zeros, that they're symmetric, right? They're symmetric across the real line. You can flip them around, and the picture doesn't change. Okay, will it be the same with the 8th degree? Yeah, they're still symmetric. Okay. Would anybody like to wager that it's going to be different for the 9th degree? Of course not, right? So now we see something. You're convinced that it's true. Through experimentation, we see, yeah, they are symmetric, but we don't have a proof. Now, to prove that they will be symmetric is not very complicated. You have to know about conjugate complex numbers and how to compute with them. And that's something that you could do with high school knowledge, easy enough, but it's still a nice observation. So of course, if we can do 9th degree, we can do more. So when I was preparing this lecture, I said, well, let's go higher. In fact, to be quite honest, when I was preparing an earlier version of this lecture from 2014, I said, let's do higher degrees. How about 20? Now do you observe anything? Okay, I'll give you a little bit of help. Let's go degree 40. Now do you observe anything? It's suspicious. They are on a circle, right? Okay, so should we do more? Let's do degree 100. Yeah, there's an outlier. The gentleman over there is pointing at one of them. Yeah, they're not all on a circle, but they're mostly on a circle, right? Okay, so let's do degree 100, okay? Yeah, see, now you need 3 fingers to point to a 4, right? So this is degree 100. I don't know if you can see. You can see that's the polynomial down here. This Morse code at the bottom, that's the polynomial. So is this a coincidence? Here's another one. Here's another one. Okay, it's not a coincidence. Now, if you are a mathematician, you will want to know why. And you will be willing to think about this for a week. Easily, even a month if needed, Yes? I've thought about the problem for 3 years. It was fun. Okay, so this is not my area, so I wanted to know why this happens. So I asked the question on Math Overflow. Math Overflow is a question and answer site for research mathematicians. And for some reason, this question got really popular. It is the third most liked question on the site. So you might think that 429 likes is not a lot. But if this were Instagram, I would be Lionel Messi with 54 million likes, 12 million likes ahead of Ronaldo, but trailing behind a picture of an egg. So now you have to go on Instagram and figure out what that is. But still, this is one of the most popular questions on Math Overflow. And mathematicians really got to explaining this. I got lots of interesting answers. And of course, they also gave me references that showed that the result is about 50 years old. I knew this was not going to be a new result. Come on, it's impossible that by drawing some roots like this, some zeros of polynomials, I would discover something amazing like that. Of course, it's old. It's about 50 years old, and probably older if you dig deeper. But nevertheless, it was an interesting experience, and it shows that you can discover some old stuff experimenting. Okay, what are we going to do next? Well, let's do something else. So far, we have been drawing zeros of a single polynomial, degree 8, 7, 9, 100. But we can do other things as well, so let's try. So let's go back to the quadratic polynomials. So the simplest one is x squared equals 0. That's the simplest one you can write down. And it's got one solution, which is 0. And there it is. It's the big yellow spot. And now, if you go on and you say, OK, how about some more complicated ones? Well, the next ones are x squared minus 1 and x squared plus 1, which we already saw earlier. And they give you minus 1, 1, minus I, and I. And I drew those with smaller dots because they come from more complicated polynomials. So then after that, you have even more polynomials with even more zeros. So the way I'm doing this is if you add up the absolute values of the coefficients here, you will always get 3. So if you look at the first one, x squared minus 1, its coefficients are 1 and minus 2. 1 plus 2 is 3. And all of them are like this. You see, 2 plus 1, 1 plus 2, 1 plus 1 plus 1, and so on. So these are the next level. We can obviously go on. And obviously, we're going to get a lot of polynomials because that's going to be, right? There's going to be a lot of polynomials. So I made my computer calculate zeros of all polynomials up to complexity 200. That means take a quadratic polynomial whose coefficients are integers, and when you add up their absolute values, you get 200 or less. It's a lot of polynomials. So wait, I wrote here how many zeros we're going to get. Well, slightly more than 10 million zeros. So you get 10 million zeros to dots like this. It takes about 2 minutes for my laptop to compute 10 million zeros, which sounds impressive. But what is far more impressive is if you watch a kid play one of those shooting games. There, the computer actually has to work hard because it has to draw tens of thousands of triangles or hundreds of thousands of triangles, maybe 50 times a second on the screen. That's really impressive in terms of computational power. This is nothing. 10 million equations is not a challenge to modern computers. Anyway, so now we're going to see the picture that comes out of 10 million of them. And to make it a little bit more artistic, instead of having these boring yellow dots, I made them look more like stars. Okay, so this is what you get. Now, if you're a mathematician, there are going to be a lot of questions here, right? So the first one is, why are there circles? You would want to know why there are circles. For the mathematicians in the audience, please observe that all these circles intersect the real line perpendicularly. So hyperbolic geometry is coming into play somehow. Who knows why, but it is. And let's zoom in. Let's just see what this looks like. So the big dots come from polynomials that are simple. The biggest one is in the middle, and that's x squared equals 0. And then on the left and the right, respectively, you have the -1 and +1, and top and bottom is -I and I. So let's zoom a little bit. And you see that there is a lot of structure here. It's very regular, so this is nice. Okay. There are a lot of the smaller dots which correspond to polynomials of much higher degree. I'm sure you could get a PhD studying this, but we're going to go on. Okay. So these are quadratic ones. Shall we try the cubic ones? I have the cubic ones, 12 million zeros. It looks like this. Okay, it's more complicated. I think it's prettier also. Yes? So let's zoom on this one. You see that there is a certain phenomena appear, like there are these dots, so everything is very circular. It's nice, isn't it? I think it's nice. So what would this remind you of? Galaxies, maybe, right? It's kind of like galaxies, right? What amazes me is that mathematicians have studied these things before they had computers, and they figured out a lot about such phenomena without ever seeing any pictures, which is amazing. We're lucky that we have these pictures. So any theorem that we manage to prove about this, say, like this week, is probably old, right? You can't easily come up with new theorems. Okay, so that was degree 2, and degree 3. But we can also do, we can do more. We can do all degrees, right? We can stick in one picture degrees 2, 3, 4, 5, 6, 7, push it as far as we can. So I have the next picture that is like that. So it goes up to degree 9. A bunch of polynomials. I can again tell you how many. It's gonna be, it's on the next slide. There we go. Now it's 26 million zeros of polynomials with integer coefficients. And let me explain the picture. So the colors are for the degrees. So yellow is degree 1, so a linear polynomial, like x equals 0 or x equals 1. Those are the yellow ones. And then as it goes towards red, the degree goes down. So orange is degree 2, the kind of yellow orange. And then the more red it gets, the higher the degree of the polynomial that produced that 0. And you can see some blue somewhere. That's degree 9. The numbers that we're getting are called, they have a name. They're called algebraic numbers, which is not surprising because we're doing algebra. We're solving equations. And there are plenty of numbers that are not in this picture. For instance, pi, or e, the base of the natural logarithm. In fact, mathematicians will tell you that most numbers are not in this picture. In a sense, there are very few algebraic numbers. And that's one of my favorite questions in the oral exams for logic and sets for freshmen. I hit them with how many solutions there are to such equations, and because I don't tell them in the lecture and I want to see what they think. Anyhow, this picture is much denser because we drew a lot more zeros. There we go. Let's zoom in on this one as well, just to see if we can see something. The various patterns are now overlaid, so I think it's harder to see anything. And it's kind of too pink for my taste. It's too full. So we should also try something else. So let's also see the blue stuff. Okay, so we're now traveling down the unit line to number 1. It's getting blue. So this is number 1. It's the 0 of the polynomial x minus 1 equals 0. And what you can see is the pinching, this pinching here, that the two horizontal things, that's the real line. Those are the real solutions. Somehow they're coming in closer. And you can see the blue things. Those are degree 9 polynomials. And they're kind of underneath. And they're smaller because they're more complex. Typically, they have many more coefficients. So they are drawn as little dots. OK, so that was fun. But it's also kind of tacky. I don't know. Maybe, I'm not sure I would want this on my wall. So let's try something else. OK, so instead of trying to draw all polynomials, we can try to draw certain polynomials, so well-chosen ones. Well, there are polynomials called the Littlewood polynomials, named so after a British mathematician who lived in the first half of the 20th century and studied them. They are the polynomials where all the coefficients are either 1 or minus 1. So here are the linear ones. Okay, so you have you can stick a minus or a plus in front of each of the powers. So you get 4 linear ones for the 4 combinations, right? Because each power gives you two possibilities, plus or minus, so it's going to be 2 times 2. And if you go to quadratic, it's going to be 8 of them. And if you go to cubic, it's going to be 16, and it's going to be 32. No, now we go 32, 64. It's growing exponentially. And let's see what happens if we draw zeros of these polynomials. And let's see how far we can get. So now we're not going to draw the circles anymore. We're just going to draw a whole lot of them. OK? So here's how many. So in 2014, I could go up to degree 26 on my computer. And then a student of mine went up to degree 30. So clearly, we have to best that. So today, we're going to do 31. Okay. So degree up to 31, that's roughly 2 to the 32 polynomials. That's a lot of equations. It's up there written. That's 8 billion equations. It's more than 1 per human, but not for long. And it gives you around 266 billion zeros to draw. That is way more than there are pixels on this screen. So we can't really draw 1 per pixel. There aren't enough pixels. What we're really going to do is, what I had to do was, I had to measure their density. So for each pixel, there are approximately, I think it comes to something like 100. I have it written here again. Where are the numbers? I might be off by an order of magnitude. Oh, yeah, 100. Yeah, it's about 100,000 zeros per pixel. Okay, that's how many we have. So what you really need to do is calculate the density at each pixel. And then you have to take the logarithm. And then you have to do image processing. And then you get a picture. Okay? So what is this picture going to look like? You already know because you saw it outside. It's everywhere. It's plastered all over the place. But it's maybe closer to the kind of anticipation you get as a mathematician when you're discovering something new. It could be extremely boring. Maybe we'll just see a circle. But maybe it's going to be interesting. So here's the picture. This takes 15 hours to calculate on my desktop. So still not very demanding. Mathematicians do much more demanding computations that sometimes take months. So this is really a toy example. But I think still it's interesting. So these are the zeros of the Littlewood polynomial. So what could we notice immediately? Well, first of all, there are lots of them gathered around the unit circle. We already knew that. I already asked on Math Overflow, why are they around the circle? And we know that they're going to be around the circle. There's a symmetry. It's still there, right? The upside down symmetry that we had earlier, it's still there. There's another one. So here's the thing. If a complex number z is 0 of a Littlewood polynomial, then 1 over z is 0 of the Littlewood polynomial that you get if you reverse the coefficients. Okay? So there is another kind of symmetry that's called inversion, which exchanges the inside and the outside of the circle. And the way you see this is if you look at a feature. Oh, you can't see anything really much here. OK. Let me see. Yeah, I think we want to turn off the lights. If you look at the feature, somewhere outside the circle, like, like bottom right, and you compare it to the feature that's inside the circle, just across from that feature, you will see that they're a bit similar, right? They're similar. That's the inversion. That's the z to 1 minus z, 1 over z. If you take a complex number and you take its inverse, if it was inside the circle, it'll go outside, and if it was outside, it'll go inside. It's called inversion. So this is another kind of symmetry, which is also notable here. Let's zoom in. Let's zoom in on those sunspots in the middle. Okay, so we're now staring at the complex number I, the imaginary unit. You can see a small white dot. That's x squared plus 1 equals 0. And then there is black space around it. So all the other zeros stay away from it, which is something that a mathematician would want to know, would want to prove. And I don't know whether this is actually proved. This might actually be an open problem. I don't know. If we have an expert on complex numbers, maybe they can tell us later. But I don't know of a good explanation of why this happens. You can ask the following. If I computed even more, so if I go up to like degree 40, 50, 100 billion, well, we can't really do 100 billion because the universe is too small. But already probably the universe is too small for degree 100. It's a lot. That's a lot of zeros. So, but if we keep going, will these black spots, will they disappear or will they not disappear? Will they stay there forever? And the answer is known. But this is 2018. So we're now in the current era. Okay? We're not in the 16th century anymore. This is also maybe worth noting. Sometimes people think that mathematicians have nothing left to do. That nothing could be further from the truth. With time, more and more mathematics is unknown. It's like the canopy of a tree. As it grows, it's bigger, right? There are more leaves where you can grow from. So anyhow, it is known that, in fact, if you calculated this to the limit, this white band would become completely white. What he proved was that it gets completely white for numbers whose absolute value is between a 4th root of 2 and 4th root of 1/2. Okay, so it gets completely white. So this is actually what we're looking at is an inaccuracy in the picture. So this is also important. When you make an experiment, you don't know whether you're looking at a theorem or just an inaccuracy, because I didn't calculate infinitely many polynomials. I stopped at degree 31. So maybe what I'm seeing is just an artifact of my experiment. So this is an artifact. Maybe we look at the fringe. Let's have a look at what's at the edge. This is, yes. Okay, so yeah, we're supposed to travel along the band and observe other sunspots and so on. Boring stuff. Let's go on. Okay, fringe. The fringe is more interesting. So this looks, I think many people would say it looks like a fractal, right? So if you've seen fractals, you're going to say, well, it looks like a fractal. So what does it look like elsewhere? So here's a little bit of it. It looks kind of like fractals. And people wondered about this. And in fact, there are some well-known fractals that look exactly like what we're looking at. So let me show you one. Okay? So this is called the dragon fractal. Take a line and fold it, like bend it like this. Okay? And now you've got two lines. And now bend each one of them like that. And keep going. What do you get? See? It's right there on the edge of the picture. Yes? Is there an explanation? Yes, there is an explanation. It was given by an Australian science fiction writer, Greg Egan, one of my favorite writers. He's a physicist by training, I think, and he does interesting math. He's nowhere near Sydney, unfortunately. So he gave a very nice explanation, which amounts to a good attack for a proof. But we don't really, at the moment, we don't really have a good proof that would explain why precisely these things are happening. Why is it that we see the dragon fractal over there? Nevertheless, we have some understanding. But the point I'm trying to make is this picture, I think, first showed up in the 2006 or maybe something like that. So when the computers got fast enough to be calculated and people observed this, and we have gone from a high school formula and the 16th century mathematics to open problems in mathematics. See, it's not that hard to get to open problems in mathematics and to understand what they're asking. So in this case, explain how these fractals are showing up on the edge of this picture. And this could turn out to be quite complicated, the answer. It's not necessarily that simple. Okay, let's go on. So one last thing I'd like to look at is, again, let's look at number 1. Because in the big picture, you couldn't really see this horizontal line. You see, there is this white horizontal line. It's very bright, which means lots and lots of zeros. This is the real line. So there's something special about real numbers here, the real line. You see that they get a lot closer to number 1 than all the complex ones. This may be an important hint at explaining why the complex ones stay away from the simple zeros. So I don't know. That's another thing that I don't know any explanation for. Why is it that the reals are they form this nice line that seems to be filling up space faster than the non-complex ones? So yes, so that's what I had to say about these pictures and the explanations, and I hope that you enjoy this lecture, and you can see why, maybe now you can see why somebody would devote their life to solving equations, and I'm going to leave you to make the decision as to whether equation solving is a science or an art. And of course, I'm just kidding with this German here, right? So Paul Klee was a Swiss-born German artist, and this is what he said, and I very much like his quote. Thank you.
So thank you very much, Andre, for this beautiful talk. Questions? So I don't want to run around with the microphone, so I'll have to repeat your question.
It's a quick double question. One, what happens if you introduce fractional coefficients? And the other one is there, I mean, everything seems to be symmetrical about the real axis. Is there some equivalent phenomenon which is symmetrical about the imaginary axis?
Okay. So the first question was, what happens if you introduce fractional powers, by which you probably mean something like x to the power of 2.7 and so on?
I was actually only thinking of fractional ABC.
Oh, fractional ABCs. Okay, yes. Okay, so that's a good question, and one, because I know the answer. So if you allow fractions, okay, so imagine that you have some fractions. If you multiply by their common denominator, all the fractions will disappear, but you didn't change the zeros. So the answer is nothing will happen if you use fractions. In fact, it's more complicated than that, or beautiful than that. If you use algebraic numbers, nothing new will happen. Right? The other question, sorry, was the symmetries. If you could.
Symmetry about the imaginary.
Yes. So we were only using the ABCs. They were always real line. They were always real numbers, and that's where the source of the symmetry is. If we used complex numbers also for A, B, C, D, then the symmetry would have gone out of the window, and I'm pretty sure there would be some way to arrange maybe the symmetry that goes this way. Yes.
I was going to ask, it looks like you're different fractals at say I and at sixth-ordered unity and at other ordered unity. Is this potential explanation for what the fractal is? Does that sort of tell you that there's a relationship between the ordered unity and the fractal? And what's the transition like?
Yes, so if you look around, the fractals change. If you look up the explanation, the discussions, so what you have to Google is the beauty of roots. And you'll get, and maybe write Greg again, but the beauty of roots will get you to the explanation. So what happens, I'm going to switch to math, okay? So what happens is that there is a family of dynamical systems parameterized by a complex number. And as you go around with this complex number, you see the fractals, the fixed points of the dynamical systems look like whatever you see at that point locally. So the answer is it is a parameterized family with one complex parameter. And as you run around, I think that's probably what you're asking, yes? Yeah, okay, yeah.
So I found the appearance of the fractals in this final kind of picture really interesting. Just wondering, with different zeros, like the Littlewood zeros, or if there's any other kind of fractals that appear in other literature that also appear in like pictures of zeros that you know of.
So one thing I know is that you could try different coefficients. Instead of -1 and 1, you could try something else like 0 and 1. And you're going to get a picture which kind of looks a little bit the same, but which has less symmetry. But it will still have the fractals around the edge. So that's one thing I know. I haven't explored enough to know in general whether other kinds of fractals will appear here. In fact, I think, so once I was trying to track down a proof that in fact we do get an interesting fringe, right? Because if the sunspots disappear in the limit, for all we know, we're just looking at an artifact of an experiment. So maybe if we go all the way and we consider all polynomials up to all degrees, maybe this is just going to smooth out and it's going to be really boring. And I don't know of a watertight proof saying, no, this is not going to happen. So that's another question here. So there are some open questions here.
Hi there. So I just wonder if there is a topology behind those singularities, because those black passes remind me of the holes in an object.
So the holes will go away, right? If we drew all the zeros, the sunspots wouldn't be there. So I'm sure there's some topology involved here, but it's hard to say in what way exactly. So I think the zeros, the holes, will have something to do with something that's a little more refined than topology. Topology is a very coarse way of trying to understand this. So I'm not sure what to say there. So maybe I don't understand your question.
Andre, thank you. As an engineer, I greatly appreciate your lecture. Thank you. Naively, can I ask, is this going to help us build a better bridge?
That's a very good question. In fact, I like the question a lot. And my answer would be this has already helped us build a better bridge. Because, as I said earlier, this desire to compute that the 16th century mathematicians had, compute the zeros of a polynomial, solve an equation, right? You can trace that directly to ever more complicated mathematics and more sophisticated ways of computing. And they actually resulted quite directly in the invention of computers. Because in the 1920s, logicians were trying to figure out what does it really mean to compute. It's not just some formulas, it's more complicated than that, and it led to computers. And I think there is no doubt that modern computers have helped build better bridges. So the answer is, yep, it's already happened.
Hi there, just another, it's a naive question. Will you release the source code that you represented in this lecture?
It's already on my GitHub.
Oh.
Yep. So you find me on GitHub, and it's a repository which is called Zeros, but it's with an E, because dictionaries can't seem to agree on what the plural of zero is.
So thank you very much, Andre, again.
Thank you.